for this
Thank you,
presentation.
Sandeep.
Yeah, and we have, he's talking from Toronto, Canada. He has obliged us for today's technical lecture. So thank you, Ganesh. And we welcome you here on this platform. And please now start your technical presentation. Thank you, sir.
Okay, thank you, Sandeep. Thank you, everybody. I think I'm responsible for this shift in timing, I guess, because 7:30 in the evening in India is about 10 in the morning here. So Sandeep was very sensitive to that. Thank you, Sandeep, for accommodating me. Before I start,
pardon me, Ganesh, you'll have to become a little bit louder.
Okay, sorry. Thanks for accommodating my timing. Firstly, before I start, I need to let you know that I'm not associated with any organization currently. So I was the CEO of ALD in India for a long time before I retired. So the presentation that I make is completely professional. It has absolutely no bias towards any organization or design or technology or equipment, which is difficult for me because I started and worked with Dynatech for over 25 years and with ALD for almost 7 years. So try to get yourself aloof from all this is a little difficult, but I'll try my best. As I said, I'm not a consultant, though I've been named one. I'm not advising anybody on any of these things. This is a purely professional pedagogic presentation. I'm also not here to talk about the details of carburizing, which I'm very sure many of you here probably know it much better than me. I'm not a metallurgist. And I also don't want to get into too much of details of even vacuum carburizing. We can do that separately. But having spent almost 35 years in vacuum heat treatment and brazing in India and a little bit around the world, and I have seen when I started Dynatech in 1984, there were exactly 3 vacuum furnaces in India. 3. One was with HAL in Nasik, one was with Myco or Bosch as it's called today, in Bangalore. And the third one was being set up in Bajaj Auto in Pune. So this is the market that I entered when I started Dynatech with a focus on starting vacuum furnaces. It was extremely challenging. Today, when I sold Dynatech, a few years back when I sold Dynatech to ALD, we were the largest vacuum furnace company in the country. I can assure you what I'm going to speak today is something that I have walked the talk. The only way you could sell vacuum furnaces against all blast furnaces and fluidized bed furnaces was not by any marketing effort because the equipment was 10 times more expensive than the competitive equipments. It is really by trying to understand what the customers would need tomorrow rather than what they need today. And I have lived that life for almost 3 decades. So I think I have some credentials to present this presentation in that format. So this is the background in which I'm presenting. I don't know the profile of everybody in this group. So there is always a danger in making a presentation to a group of 50 plus people when you don't know who they are. But I'm assuming since you attend this seminar on a Saturday evening at 7:30, you have some interest and knowledge of carburizing or heat treatments. And I will assume that when I make this presentation, without getting into details. Everybody knows carburizing, which is adding carbon onto the surface of the steel. Typically, it's done with transmission components and other engineering components. When we started low pressure vacuum carburizing in India, as Sandeep said, the first process was done by Dynatech when we decided to do it independently. This was somewhere in 2008. I knew there was one company very close to my office in Bombay, which already had installed the vacuum carburizing system, and that was Mahindra. And that's how my connection started, first with Sunil Kale, and with Sunil Kale, it went on to Sandeep and the team. And we all understood vacuum carburizing, but they were using it. But by the time we could consummate that process, we were acquired by ALD, and ALD was the world's largest vacuum carburizing equipment company, so it became easier for us to introduce. But now again, I'm going to talk of something else, which is tomorrow's world for organizations and businesses in the heat treatment, specifically on carburizing. The question is, most of the time when we are running a business or working in a company, the pressures of focusing on today are so large that other than a specific department like a futuristic planning department or a manufacturing engineering department, which thinks about tomorrow, most of us are on a day-to-day level, managing from crisis to crisis or cash flow to cash flow. I think we need to step aside, zoom out, and see whether we can get engaged in tomorrow. And there's a reason why we should do this. What is my role in my company or in my business if I run a business? Basically to handle today's issues and opportunities. Is that so? Is the question. I remember when I was in my 80s and I was working for a consulting firm after my MBA. I accidentally stumbled on this book called Future Shock. It was written by Alvin Toffler. I read it like a normal book you pick up at an airport when you're flying. I wish I had read it like a textbook. Because the remaining 30 years of my life in corporate was all a series of future shocks. I think first future shock in India was 1991 when under Narasimha Rao we liberalized the country. And since then, everything has been a set of future shocks, the internet, the cell phones, and so on and so forth. I would recommend for many of you, if this book is still available in Amazon, if you can get a copy of this book, share it or read it, it will prevent your future shock. Because future is definitely there. Our objective is to prevent it from becoming a shock. I strongly recommend this, and that's why I bought this out. The question is, what is your future shock? Tomorrow is your future shock. And how do we prepare for tomorrow? And we narrow down to carburizing in a while, is the key to this presentation. Can we predict tomorrow? Many people try. But this is something like the difference between climate and weather. Climate is what you expect, weather is what you get. Tomorrow is what you predict, but today is what you have to handle. And before tomorrow becomes today, if we prepare for this, we will be all better off in any field, and specifically in heat treatment or public. Day-to-day job involves working with the hows of today. And when we keep working with the how to do this, how to solve that, how to prevent this, how to handle this, how to attend a meeting, how to make a presentation, how to make a proposal, how to solve a problem, the hows of today gets us into a what. And if we continue to remain only with the hows, within a very few years or few time period, we will all be shouting for help, trying to save ourselves. I've been through this process, running Dynatech many times, and I'm sure many of you have been in this situation of trying to save your skin most of the time. Whether it's a problem customer comes up with, whether it's your own cash flow problem, whether it's handling a vendor, handling a technology. It's a lot of SOS from morning 9 till evening 6. And we want to prevent this. It doesn't make a good career or a good job. Instead of focusing on the hows, if you start focusing on the whys of today, you can start the wave tomorrow. And it's this shift in mentality between the hows to the whys, not only in general management, but specifically in heat treatment and carburizing, that it will help all of us move forward. Of course, many of you will say these rhetorics are all fine, but tell me what I should do today, what can I do today in the field of heat treatment or in the field of equipment maintenance, planning that will help my future or my company's future. Precisely. The first thing we all need to think of is to get a mindset change by saying, let's engage with tomorrow. Let today not limit you. And these are the issues that we will be covering very quickly. When we shift our focus from the how of today to the why of tomorrow, this will automatically happen. I'll start with the first field of tools heat treatment. This is a field that I encountered personally in the 80s. If you had tools, high-speed steel, hot work die steel, cold work die steel, H13, H11, D2, D3, the typical today's house were in the 80s were steel quench furnaces. Sorry, salt bath furnaces. The moment you have salt bath furnaces, you have toxicity issues, you have heat loss issues, you have cleaning of tools issues. You have hundreds of things that came post the heat treatment, which was challenging. Then a salt bath furnace could be done for less than ₹1,00,000. And the only other technology of tomorrow that was available was what we were marketing, which was a vacuum heat treatment, would cost 50. So the 50x factor, the investment of shifting a full scale heat treatment from salt bath of fluidized bed to vacuum. Obviously, not an easy job. No manufacturer would be able to convince a customer to invest 50 lakhs, that's 1 lakh that would do the job. And technically, there was nothing wrong with the salt bath heat treatment because we have a very good result. But today, I don't think any of you disagree that anybody goes for salt bath heat treatment anymore. Full heat treatment is predominantly vacuum heat treatment. And so 84 to 2020 is not even 35 years. And this happened even 10 years back. So within 20, 25 years, we could see a big mindset change of the whys overpowering the hows and the vacuum overpowering salt bath. This is a classic example of something that would apply in case of carburizing tomorrow, if not today. We can discuss in detail this later. So the why of yesterday became today's vacuum. And this is something we need to appreciate, look forward to covering. Like any field you look at simply on space travel. Yesterday is how, when you talk of space travel 20 years back, you would think of astronauts and rockets. Today, when you talk of space travel, you talk of Blue Origin and VSS Unity. Non-astronauts, simple, ordinary layman people are going to space and coming back within a few hours to 5 minutes. It's just a mindset change. It takes a Richard Branson, it takes a Jeff Bezos, it takes all these guys to change a mindset, and space travel can change. If space travel can change, you will appreciate carburizing can change and will change. Today is how frequent furnaces, continuous gas carburizing pushers, and so on and so forth. Who can compete with these? Do they do the job? Of course they do the job. Why would anybody look at anything else which would cost 5 times more investment or 10 times more investment? Why would any company in Germany or France or Italy, why would any company in the US or UK ever plan to invest 5 or 10 times the investment? Because that logic of investing more to get the same result is the same whether it's India or the US or Germany or France or Italy. The fact that others are doing it is because they have started looking at the whys of tomorrow rather than focusing on the hows of today. And I think it's only when you do that, you will be preparing yourself for tomorrow. Again, today's whys should be different, and they are different. So it's not your job today or business today. I remember going for a meeting in Hosur once. This was about 7, 8 years back before I retired, 1 or 2 years before I retired. I visited this company and I was talking to a general manager designated level person. And he told me, Mr. Ganesh, you have about 30 minutes available to convince me that I should make my company invest in a vacuum carburizing when they already were running a battery of steel quench furnaces. I was pretty quick on that day and I said, you know, Mr. So-and-so, I'm not going to try any such thing. I'm not trying to convince you that you need to shift from this to this. If you have not felt it important to shift from this to this, I would be the worst person to convince you to shift from that to this. And I think this is the situation many of us will find ourselves today. Whether you are an equipment manufacturer, whether you are a heat treater working for a large company, or you're a businessman running your own heat treat shop. How could you expect an external agent, especially a vendor, to convince you about something which you yourself have not felt it necessary or important? But you know what is the fundamental difference here? If you don't look at it from that perspective today, it will become your perspective tomorrow. And that time, it would be too late. And I will give you examples of that happening in Indian reality situations. My suggestion to each one of you, I mean, becoming very professionally without being part of any organization, is to engage with tomorrow today. Because today's tomorrow is going to become tomorrow's today. And the kind of problems you will face tomorrow, become tomorrow's today, are going to be a lot more difficult if you're not prepared for it and not engaged with it. Now, I'll give you real examples of all of this as we go forward. Just setting the stage up for it. Before tomorrow becomes yesterday, make sure you think.
Excuse me, Ganesh. Again, sorry to disturb you. Your voice is low. I'm getting a lot of complaints on the chat. Please bring the microphone closer. Probably that will help.
Okay, is this better?
This is much better.
Okay, I'll move forward a bit. Sorry about that. So basically what I've been talking about is trying to think and get engaged with tomorrow, because tomorrow is going to become today someday. It is also going to become day before yesterday someday. Before all this starts happening, get engaged with tomorrow. Now, for most of you who are working, remember your career, or even for those of you who are in business, your business or your career is not only just today, but 25 years plus further, depending on your age or the position you are in. So most of your work should be, of course, related to today, but there has to be an element of the next 25, 30 years built into your structure of your work from 9 to 5 or Monday to Friday. And if you don't do this, tomorrow will catch up with you, and that would not be very happy. Coming back to carburizing, which is what we are all gathered here to listen to. It's easy to stay with atmosphere carburizing. We all understand it very well. It's a old technology. Everybody is comfortable with it. We know the problems associated with it. We know how to solve these problems. We know the end result comes. We know if you're carburizing a gear of 0.6 mm case depth, you will get it. And none of your OEM customers or tier 1 customers to whom you supply the component are ever going to complain because you carburized in a seal point furnace or a CGC or even a pit furnace for that matter. So nobody's going to complain, but that's because everybody's focused on today. But it's going to be not very long before these would become unacceptable, just like salt bath became completely unacceptable for various different reasons compared to vacuum for tool steel. It is difficult to shift to vacuum carburizing. Let us not make a joke of it. It's not easy. Not just the investment of 5 or 10 times, but the whole mentality that you need to vacuum carburize, as people who are running it for many years, like Sandeep will tell you, it requires a complete plant mind shift. It's just not you as a heat treater who has to shift. The entire facility has to shift. The maintenance team has to shift. The project management team has to shift. The management team has to shift. It's a gestalt approach. And so let's not look at it as one equipment substituting another equipment. It's a management process that's changing completely because you're not focusing on what your customer needs tomorrow, not today. Again, engage with tomorrow, the first step. Let's go to today's carburizing, the typical house of today's carburizing. One of the first concerns when we have as a B2B business, and I've written a textbook on B2B marketing based on my experience, and I can vouch for it. We all believe when you're selling commodity processes, like carburizing is a commodity process. Everybody knows carburizing, everybody can carburize. So what is it that you can do better than somebody else? Why is my carburizing better than somebody else's carburizing? So the customer is now going to pay you 1 dime more to carburize a gear or a shaft to 0.8 case depth. If somebody is giving it to him at 36 rupees a kg, he is probably going to look for somebody at 35 rupees a kg, not at 40 rupees a kg. This is understood. So this will be the first how of today's carburizing. I cannot shift. My customers will not pay up. Customer will not pay more. I had a very interesting meeting in Timken about a few years back in Bangalore, where they have a huge R&D center. And it was interesting, even a company of the stature of Timken had a serious challenge when they were not doing the carburizing themselves, they were giving it out. But without Timken's blessing, one couldn't go to the vendor. And when one was approaching Timken, it was a big challenge to convince Timken the merit of paying more for carburizing. I'll get to that later. Same thing, the cost per kg is a driving criteria in carburizing. especially if you're a commercial heat treater or you're giving your work out if you're an OEM. The cost per kg. Now, what constitutes the cost per kg is a different ballgame. Many people don't have the patience, or I would like to say even intelligence, to get into the depth of understanding what is the cost. This is where the difference comes, and we'll talk about this. Investment is very high. A steel quench furnace can be bought below 1 crore today. And if you want to go for a vacuum carburizing, you're spending 5 or 6 crores or 8 crores. Who can ever justify an investment of 5x or 8x just for some benefits for tomorrow? Difficult. And finally, the thing that we are all talking about, the Trumpian adage that climate change is a hoax. It doesn't affect us. Bombay is as hot as it is, as it was, as it will be. We don't believe climate change exists. Now, all these things put together makes the today's house very acceptable and tomorrow's wise very challenging. But I'll tell you the reason why we should start thinking why we should look at an alternate technology to conventional carburizing, which is low pressure vacuum. I'll give you an example of why a company which didn't do this at some time had to literally close down their business. I've seen that happen. You may not have a business tomorrow if you don't do this. Electric vehicle specifications today, if you are a supplier to Tesla or any of these companies, they insist on the technology that should be used for carburizing, if carburizing is one of their processes. I can give you an example of that right in India. So electric vehicles, which are coming in a big way, and we'll talk about that later, would demand a different kind of carburizing, whether you want it or not, whether you can afford it or not. Whether you believe it or not, we will all finally come to accept climate change. Just as it took 2 waves of the coronavirus in India to realize this pandemic is genuine. When we had the first wave, we got away with it in India. I was in Canada and we got hit very badly in North America. But by the time the second wave came in India, we know India became a tragedy story. Sitting here in North America, I felt bad at the way people were talking about India. So we know climate change exists, we can deny it, but we all finally will realize it will impact us, each one of us. And tomorrow's world, again, is completely focused on decarbonization, which is reducing the carbon in the atmosphere, which is different from ozone depletion. And when you have to live in a decarbonized world, how do you fit in the oxymoron of carburizing, which is adding carbon? And this is a tricky situation which we all have to be prepared for. These are the whys to consider when we move into vacuum carburizing. Tomorrow's carburizing, which is the low pressure vacuum carburizing, is completely focused on the marketing axiom that you need to satisfy customers. And who can deny this or who can disagree with this? Friends, customer satisfaction is the primordial basis on which any business is built. Those of us who can think of customer satisfaction before the customers start thinking of it would be successful. I don't think any of us asked for WhatsApp. I don't think any of us asked for the internet. I don't think any of us asked for the email, but there were people who thought we needed it before we even thought about it. Those are the successful companies of today. If you can be a successful company tomorrow, you need to think about what your customer is not thinking about himself tomorrow. And in carburizing, that would be a decarbonized world carburizing. That would need low pressure. Climate change is happening, whether we believe it or not. And how do we carburize in a climate change world? Reliability, documentation, and verifications were a part of the ISO process we all went through as part of a process. But I think we're all reaching a point, and I'll give you an example of a company in India where this verification and reliability was the only reason they moved to vacuum carburizing and the damage they had to face with conventional carburizing. And how do we all build technologies that are sustainable? I think we all live in a world, we want to live a better world for our children and grandchildren. How do we live a sustainable world for the future generation? All this put together are the whys of tomorrow's carburizing, which is low pressure carburizing. Some of the people would like to still believe electric vehicles will never come in India, where are the charging stations, and so on and so forth. you will be very surprised at what the trends are happening around the world, and it's a matter of time. There was a time in India, which I think Sandeep and people of my age and vintage will remember, when we had to get a telephone connection from Bombay telephones in Bombay. It would take us 10 to 15 years wait list. And suddenly we jump past the entire landline system and got away from the copper laying cables, went on to mobile, and India today is one of the largest mobile connected countries. You have no idea how things can change so fast. Like telecom is a classic example of how technology could override these expectations and how the wise will get better than the house. And electric vehicles is a case in point. The other thing we all talk about is carbon emission is a developed world problem. Of course, it has been a developed world problem. Most carbon emissions came from the Western world. But today, it's all happening in China and India. And we will all be pressurized to move into a decarbonized world. And how do we live in a decarbonized tomorrow and carburize? And the last part is high investments are not good. Because we all come from a mindset. I remember when I was in my 80s trying to do investments, interest rates in India were phenomenally high. I remember even borrowing money in Dynatech at 18 and 19% per annum interest rates. I think today we all agree. I don't know what the current RBI bank rate is, but I believe it's about 5% or something. Because inflation has come down. And as macroeconomics tells you, when gross inflation comes down, gross interest rates come down, and retail and corporate interest rates come down. So when you are investing at 19% interest rate, you could not afford to invest. But today at 9 or 10% with corporate interest rate, capital output ratio ensures that you can take care of technology with better investment. And I'm sure all of you are looking forward to that. Make sure tomorrow you can ride the wave and not get caught in the carpets. That's what the whys are. Let's come to carburizing as we understand for tomorrow, which is low pressure vacuum carburizing. The fundamental difference between conventional carburizing and low pressure carburizing is that you provide a calculated carbon supply into the furnace. Unlike the conventional carburizing where you just end up passing methanol or endogas on a continuous flow rate per hour or per minute. It is not a calculated carbon content. In vacuum carburizing, you actually calculate the carbon content, and I'll show you in the next slide how it is done. Now, this ensures there is no excess carbon, unlike excess methanol, excess endogas. So basically, fundamentally, you get no soot on the components. Secondly, you get absolutely no CO2 coming out of the exhaust. In fact, the only exhaust you get is water vapor. The process is typically done under vacuum. Now, vacuum definition is 1000 millibar absolute or 760 torr absolute. Anything that you go below 760 torr or 1000 millibar would be technically vacuum. So carburizing is always done in partial pressure, which is vacuum, which means there is no oxygen. Because the advantage of vacuum is, the air that we breathe in the room that we're all sitting in today is 20% oxygen. 20% oxygen is 20,000 parts per million oxygen. So when I come down from 1000 millibar, which is the atmosphere, to 1 millibar, I have brought it down to 20 ppm. When I bring it down to 10 minus 2 millibar, I have brought it down to 0.2 ppm. So by reducing the concentration of oxygen in the atmosphere in which you heat the steel or the component, you are reducing the oxidation or preventing the oxidation. And thereby, you get absolutely no intragranular oxidation when you carburize using low pressure vacuum, because its whole system is under vacuum. The second advantage of doing it in vacuum is the laws of physics hold good. Every time I achieve a 7 torr or 8 torr or a 10 torr vacuum, then the laws of physics of Boyle's law will hold good because PV by T is constant. So every time I get a 10 torr pressure, I can be assured of a certain concentration of lower concentration of oxygen. And this process can be repeated repeatedly, which means I can have a reliable and repeatable atmosphere, which I can never ensure having a flow of methanol, nitrogen, or endogas. This is a huge advantage when standardizations get into a big kick, when you get into organizations which are very large, which depend on documentation to prove every cycle and batch that you've done. Thirdly, because the systems are now under vacuum, the furnaces are designed and capable of going up to 1320 C or 2400 F. Because typical vacuum heat treatment furnaces for tool steels are designed for 1300 C. So the vacuum carburizing furnaces are also can go up to that level, so you wouldn't use it at that level. But it allows you to even now carburize the conventional 16 mm CR5, the conventional 20 mm CR5 steels up to 980 degrees C compared to 930, 935 that you would do in a conventional. This increase in temperature from 930 to 980 itself saves you tremendous savings in cycle time to achieve the same results and thereby get a larger output. And of course, all of us, when I was an ALD, and most of the companies that are in vacuum carburizing equipment today also manufacture the same furnaces which can go up to 1080, 1090 degrees C. We call it high temperature carburizing. But keep in mind, these come with a caveat. And the caveat is that the steel has to be different. You need to ensure there is sufficient vanadium, nitrogen, and aluminum in the steel. Those doping agents are needed. Otherwise, you end up getting a lot of crystal growth in the steel, and you don't accept that. So yes, high temperature carburizing is possible. Cycle times can be reduced. I remember in ALE, we used to sell a system, not in India, but elsewhere, where you could do a 0.6 mm carburizing in less than 36 minutes. That's a shocking number, keeping in mind that 0.6 mm paster, the conventional 16 mm CR5 steel in silk quench furnace could take 3 to 4 hours. The process gas that is used to supply the carbon in the carburizing furnace in low pressure vacuum carburizing is typically acetylene, compared to methanol or endogas, which is used in conventional system. Now, the advantage of using acetylene, that everybody uses, there's nothing proprietary about it, is that it gives you very high efficiency of carbon removal from the gas compared to endogas or methanol. The quantity of endogas, quantity of the acetylene that you need to process is very, very little. These furnaces are all typically graphite-lined furnaces. And graphite is a very low weight, low thermal conductivity material. So it provides very low heat loss at a steady state temperature of 980 or 990 degrees C. In fact, if my memory serves me right, I've been out of it for a while now, at 980 degrees C, a steady state equilibrium vacuum furnace would probably give you somewhere close to 5 kilowatt per square meter thermal heat loss. Compared to a refractory brick, which normally lines a steel quench furnace or a CGC, would be somewhere around 14 to 15 kilowatt per square meter. We're talking of huge energy savings here. Coming naturally out of the materials of construction of tomorrow's carburizing systems. Secondly, because these are very, very low mass products, it's very easy to shut down and start up these lines. If I was to ask Sandeep to shut down his CGC in Mahindra Kandivali, it would take him, correct me, Sandeep, it will take me a day or two to shut it down, and maybe equally more to start it up. Am I correct, Sandeep? Okay, he's muted off. You could, three days? Okay, yeah, I thought so. I'm being nice to you. It could be done in a few hours with these systems. Now, you would wonder, why would you ever want to shut down and start up CGCs? You wouldn't, unless you had some maintenance issues, or an emergency, or you have a batch size changes. Now, when batch size changes happen, you would like to recondition the furnace atmospheres and all these things. Everybody who runs these systems know about it. It's a huge advantage that you have. The gas flows are pretty well regulated. I'm sure today's CGCs and SQF also have these regulation capabilities, but the vacuum furnace demand them because we're dealing with small flows of acetylene gas. And the flow of gas here is an extremely different kind of flow rather than a motorized valve or a solenoid valve flow. These are all pulse flow, and I'll make a sketch of this and show you how this pulse flow works. It's a pulse flow with an incline, where you can adjust the amplitude of the flow the frequency of the flow, and the incline of the flow. And it's a very interesting concept, which makes a huge difference in preventing sooting and excess carbon deposition on the surface of the flow. Of course, these systems are all PC-based, algorithmic driven. So basically, these are kind of an artificial intelligence-based systems where the steel itself, just the programming the steel into the program sets up the parameters for the process. It removes the skill set out of the operator. It brings it back into a repeatable process. If you were to ask me as an independent person, not part of any organization, purely as a proponent of this technology, because I got involved in it much earlier than many of you, this is the technology that provides the lowest operating cost for any carburizing system. You can compare it with SQF, you can compare it with CGC or a quick furnace. No other technology, with all the benefits that it gives you the lowest operational cost per kg of a component. Where the arithmetic changes is purely when you bring in the depreciation and the interest costs coming from the larger investment. But we'll talk about that differently. So this is the ethos of tomorrow's why one should even consider looking at tomorrow's technology. Now, the moment one thinks of low pressure vacuum carburizing, because one of the companies that was pioneer in this, building this technology up substantially was my ex-company. I think the company where Mohinder now works. Is they developed this technology exclusively with gas quenching. Now, obviously, helium was the recommended gas because if you were to remember your periodic table classification from your engineering college, you remember the smallest atomic number is 1 for hydrogen, but you don't want to use hydrogen for obvious reasons. So the next one is helium, number 2. And so these were all using 20 bar helium quenching, which is what most of the technologies are. But I would like to show you today, most companies have also moved away or can offer vacuum carburizing with oil quenching. But even when they offer oil quenching, remember that oil quenching is also under vacuum. And in fact, when I was in ALD, as the CEO, we developed the first vacuum carburizing with oil quench built in India, and we supplied that equipment. So we have done this. It's working for the last 8 years. The last time I spoke to the client in Chennai, it still operates. So even though it's possible to do quenching with gas, helium, but the moment you use helium, the caveat is you need a helium recovery system because helium is so expensive. And then there are issues with helium. You have, with acetylene, when you use for carburizing, you have DMF and acetone base. So a lot of caveats come with all these things, but you need to be sensitive to all this. The right equipment provider will give you all the benefits of the advice. But if you use oil quenching, you don't have to touch anything with your steel. You can still get your core hardness and surface hardness, mostly surface hardness, that you would need. This is done with using nitrogen gas as a blanket material so that there is absolutely no possibility of oxygen or air infiltrating inside. When you talk of quenching, whether it's helium or nitrogen or argon or oil quenching in vacuum, there is always going to be distortion. And one of the panacea that people expect and bad marketing people try to market low pressure vacuum carburizing is to say there is no distortion when you use vacuum carburizing. I would like to personally advise you, any steel, anytime you take any steel machine product to high temperatures, austenizing temperatures, and then quench it by natural thermal forces, there is going to be distortion. It is difficult to assume that there will be no distortion by laws of physics or heat transfer because you're heating something to such high temperatures and then quenching it. The very process of quenching means there's going to be differential temperature on the surface and the core, and that will bring distortion. The difference between quenching in these systems and in conventional systems is that the quench patterns can be set so that the distortion levels can be repeated. And when you can repeat a distortion level, you can adjust your soft machining so that you can counter the predictable distortions. So you end up having virtually no distortions when you finish, and you probably don't need a post-treatment machine, no hard machine, which is a big advantage. But this is not something that will happen automatically. I remember in at least 15 or 20 cases, I lost business in India because I would not guarantee the customer when I was an ALD. I would not guarantee the customer no discussion. The customer was wrongly informed by other competitors that if you buy low pressure vacuum carburizing systems, you would not get distortion. And I, as the CEO of my company, did not want to guarantee something which was not possible by laws of physics. And I lost those business. And I had some problem with my board and my CEO in Germany. But I could convince them this was in the long-term interest of the company. And finally, we won. We got the order back. So the company in Chennai, because they realized later in life, when their house became wise of tomorrow, they understood the technology better. Even the transfer of the product or the component or the grid from the furnace hot zone to the quenching is under vacuum. And so there is absolutely, again, no contamination of oxygen when you transfer again using nitrogen. It's all under partial pressure. Because these furnaces are using graphite insulations and have very little moving parts, the overall dimensions of these hot zones and furnaces become very small. And because they become small, the floor space of the area layout you need to put up this line becomes very small. If you were to visit and see a CGC line, you will realize it takes a lot of space running linear one way. Or even if you have a battery or SQS, you'll see it takes a lot of space. Continuous vacuum carburizing furnace line takes very little space, and it's a very clean space. Lastly but not least, if you want to change batteries, you want to change the steel types, you change the components, change the K-step, you want to change the cycle. These are all very, very quickly changeable without having to condition the furnace over long periods of time. So how does one factor all this in when one takes a decision on taking vacuum carburizing compared to conventional carburizing? It's impossible to expect a general manager of a company or the owner of a small heat treatment shop or an engineer in a maintenance or in operation or manufacturing engineering department to be so knowledgeable in all these things that he or she would factor all these things and take a right recommendation to its senior management on investing in vacuum carburizing. Almost impossible. Because nobody is going to lose their job because they did not recommend something for tomorrow, but they will definitely lose their job if they recommend something that costs 10 times more investment and somehow it doesn't work out. So who wants to build a cat? So most people in organizations, I have found when I met clients, but we're finding it very difficult to present their case to the next level of management. If you're in this equipment business, that's a big challenge. And if you're the other end of it, you're the one who is doing it, you would always wonder, why should I listen to Mr. Ganesh and try to make this proposal to my senior management when I have very little to gain? Because by the time the gains come, it will be 5 years down the line, 10 years down the line. This is where the difference comes. If you are a middle management person, you're still going to be working somewhere 10 years down the line. And it would matter to your career and your life if you did this now than 10 years later. So I think there's a huge advantage, but these are very difficult to monetize, very difficult to factorize into the decision making. And this makes the marketing of these things extremely challenging. But here, my job is not to market, although I don't work for any company anymore. But I want to make sure the procurement of all these technologies, the thinking of all these technologies is a lot better understood. So the marketing people don't have to do their job. You would then become a better person in buying these technologies for your own future. Let's see how these things are calculated. This is not a detailed thing, but it's a very short thing, just so that some of you who are a little more interested can look at it. If you were to take a gear would have a certain OD and an ID. It would have a certain height. So with the software, you can always calculate the surface area of the gear on the top and the bottom, the inner area, and the toothed wall. So let's say you calculate the surface area and you get a certain millimeter square. Let's call it A millimeter square. You want to achieve a certain case depth in carburizing. Let's call it B millimeter. So you can actually calculate the volume of carbon that you will be depositing, which is nothing but the surface area square millimeter square into the case depth millimeter, and you get the carbon volume in millimeter cube. That's the volume of carbon you need to bring into the equipment. So once you have the carbon volume calculated, which can be done with an algorithm for every component that you have, a shaft or a gear or a blank or whatever it is. Carbon has a certain density at a particular temperature. It's grams per millimeter cube. So you know carbon at 980 degrees or 930 degrees will have a certain density. I think if I'm not wrong, my memory, purely memory tells me it's 5.2 or something. So you have the volume, you have the density, you can calculate the mass of carbon that you need to bring in. So you get the mass of carbon in grams or kgs or whatever grams come. Now, if you take acetylene as your feeding gas, which is what is used in vacuum carburizing, acetylene's formula is C2H2. It's 2 gram moles of carbon to 2 gram moles of hydrogen in 1 gram mole of acetylene. Carbon's atomic weight is 12. Hydrogen's atomic weight is 1. So if you have 2 gram moles of carbon, you will have 24 grams of carbon. And if you add the 2 grams of hydrogen, the total 4 grams of hydrogen, you will have 26 grams in acetylene. So you realize out of 26 grams of acetylene, 24 grams is carbon, which is what you wanted in the system. So you actually have 24 grams of carbon if you introduce 26 grams of acetylene. So you know the carbon mass you need to bring into the system. If you divide it by 24 and multiply it by 26, you will know the mass of acetylene you need to bring in. And that is transferred into a mass flow transducer. And this is transferred not in one lot, but it's transferred with certain amplitude, certain frequency, over a certain incline. So you can grade all this thing very well. But that is the design calculation of the carbon into the system. You realize the utilization of acetylene is to the extent of 92%, 24 out of 26. You think of a process which is so scientifically designable. This is tomorrow's process. This is the why of tomorrow, where you get an inherent 92% capability to transfer carbon from the medium to the component surface where you want to cover. If you look at conventional carburizing, you typically, let's take the example of methanol. You can use endogas, which is components of things. Let's take methanol. Methanol is CH3OH. So again, you have 1 gram of carbon, 4 of hydrogen, and 1 of oxygen. So for 1 gram mole of carbon, which is 12 grams of carbon, which is the atomic number 12, you have 32 grams of methanol because oxygen is 16. So you realize that your inherent efficiency of carbon transferred from the medium to the component is 12 by 32, which is about 36, 37%, compared to 92%, which is the inherent quality of transfer of tomorrow's carburizing. Today's carburizing is 36% inherent. So you can imagine the amount of methanol you need to pass. It's inherently designed to pass 4 times, 5 times more methanol. And since methanol is not passed alone, it's passed with nitrogen. Or you need to compensate it through endogas, which is a mixture. So when you pass methanol or endogases, you're going to end up getting exhaust. And the exhaust will, of course, be H2O because it has got hydrogen. Of course, it's going to be carbon because you're passing excess methanol. So it's going to be CO2 and CO. When you are using acetylene, you had C2H2. The C2 was a calculated C2. So there was a preferential deposition of the carbon on the surface of the steel, leaving behind only H2 in the residual. So whatever was coming out of a low pressure vacuum carburizing was just water vapor. Here you do have water vapor, but you also have CO2 and 2. Hey, climate change. As I told you, whether you believe in it or not, you're contributing to the carbonization of the world. We want to go and live in a decarbonized world. You're building. My friends, without getting into further details, as I know I am getting out of time another 10 minutes, it's actually the lowest operating cost system. Whether you believe it or not, I can prove it to you. The whole process is a designed process. It's not something that is left to a flow rate or a chance. Guarantees no carbon exhaust. It's the most energy efficient system because A, running in vacuum, B, you're using graphite as the insulation because these are continuous systems. They're constantly generating 4 to 5 kilowatt per square meter compared to 14 kilowatt per square meter. Huge energy saving. I'm not saying there is no distortion, but it's a controlled and repeatable distortion, which you can be handled by soft machining. Completely built-in tracking and verification process. You have components which are extremely clean, other than when you use oil punching, when you need to clean the oil, with absolutely no IGO. In fact, in the continuous system, you can take the components and send it for assembly. You don't need any post-treatment cleaning or washing or machine. The facility itself is a clean, compact facility. Your heat treatment shop can be put right in the machine. You don't need a separate heat treating facility because this is like a machine. It's like a CNC operated water cooled machine. The external levels of the chambers are all water cooled. It's cold. I'm giving you some examples of companies that have adopted the whys of tomorrow day before yesterday, even today. Delphi comes to mind, Mahindra, of course, we talked about it. Fiat is there, Tata Motors, Sonacom Star. There are a couple of others whom I sold to also. Now, what is it about these companies who did not think about the 5 times more investment, who did not believe in climate change? What is it that they made and when this made this investment? A lot of it came out of their customers or their parent companies. And on their parent companies, whether it's Fiat or whether it's Delphi or whatever it is, it all happened because their customers demanded it. Now, before I conclude, I just want to give you 2 examples. I won't name the companies. About 10 years back, I met a company in Manesar, Gurgaon. I have 2 minutes or 5 minutes, Sandeep?
You can take your time. Ganesh, there is no hurry. You can take your time.
Thank you.
Yeah.
Thank you. I visited this company, and this is what giving us point across. I visited a company in Gurgaon, if I'm not wrong. It was a typical, no offense to anybody, but typical North Indian company. You know what I mean? Since many of us are from Bombay, we understand the mindset difference. He invited me, I landed up there, and when we started talking, I realized the person I was talking to was a vice president kind of level. Now, in different organizations, designations don't mean much. If the company is a proprietary type of company, the vice president doesn't have much authority, it goes right up. Of course, if you're at a Mahindra or somewhere, the vice president is a big guy. He has authority. So within about 20, 30 minutes, I realized there was a point beyond which talking to this guy about the macro stuff wouldn't matter. So I tuned my channel off and started talking about technology. Now remember, I'm not a metallurgist. I'm a chemical engineer by design, but then I moved into marketing or business. So I started talking about technology, carburizing, and I kept this guy rumored for about an hour. And after all this was over, I was taken to the next level, which was the owner of the Lalaji. And that guy asked me one simple question. If I had to buy your equipment, Mr. Ganesh, what would it cost? Now, if in the first day of a meeting, if a customer is asking you the price of your equipment, I have enough marketing experience to know this is a bad show. And there's no point wasting my time here. So I told him, sir, I don't think I want to give you an answer to that question because I don't think you are ready to buy that equipment. And this hurt his ego, obviously. You tell the owner or promoter of a company, you are not equipped to buy my company, that hurts him. But this was my trick, it always worked. So I told the guy, I'm sorry, sir, I don't think you guys are ready to buy this technology yet. I didn't tell him my equipment, I told him this technology. He said, why do you think so? I said, I don't think you've asked me all the right questions yet. He said, tell me what are the questions that I should ask. I said, I cannot ask the questions on your behalf, but I think we should meet some other time. So to cut a long story short, we never met for a while. After 1 year, I was invited by the same company again. I think this was in 2011 or something, and then I went back in 2012. We had a very detailed presentation of the technology. In fact, I had a German technical colleague with me, and we spent almost a whole day there. We upgraded their knowledge on vacuum carburizing. Purely technical, no commercial. No question around, we didn't meet the Lalaji, only technical. We were invited again in 2013. Further discussion, trials were done for them in Germany. Components were sent back. They were very amazed to see the results, but they were disappointed with the distortion. Disappointed because they expected no distortion. We never told them that. And we told them this is a good learning curve for you, you should expect distortion. But we can assure you the same distortion will come second time. They sent us more trials, we did more trials, we sent the components back. Again, there were distortion, but they were exactly the same identical distortion. 3.5 years of padding. I was not even willing to give them a proposal. Because I believe they were not ready for the wise of tomorrow. They were still struggling with the house of today. 2016, I retired. 2017, if I'm not wrong, they invited, they called me. They still had my number. And I was already in Toronto. I remember they calling me at about 3 in the morning. It was 3 in the morning in Toronto. But I recognized the number. I called up. He was a very good friend by then. I picked up the phone. He says, Mr. Ganesh, I want to talk to you. Can you come tomorrow? I told him I'm not in India. I'm in Toronto. I can't come tomorrow. But anyway, I'm retired. I have nothing to do with this business anymore. He says, no, you can't do that. I said, I've done that. He says, okay, what do I do? I'm ready now to buy the equipment. We need to start discussing proposals and commercial. I put it on to my colleague in Germany. My colleague had also left ALD. He joined a competitor. So I said, listen, my colleague has also left the company, but he works for a competitor. Is it okay? He said, okay. Put it on to my colleague. 2017, they met. 2018, and the equipment was ordered. 4 million euro worth of equipment was ordered. You know why? Not because they fell in love with vacuum carburizing. Simply because they were prepared for tomorrow. They were engaged in tomorrow. They were a component supplier. They were supplying automotive components. So long as they were supplying to the Honda and Tata Motors and Suzuki and all these things, there was no pressure on them to change. But they were still engaged in tomorrow for 4 years. Suddenly they got a huge inquiry from guess whom? Tesla. Tesla's inquiry had one subline in that specification. That subline said components must be carburized in low pressure vacuum carburizing equipments. Just one subline. And they had a window of 72 hours to make a proposal for that quote. They were engaged with tomorrow for 4 years. They could complete a proposal in 24 to 48 hours. They submitted the proposals compared to global suppliers. They got the order of those components. They bought the equipment worth 4 million euro and they're doing business today. I spoke to that guy even 2 weeks back, 1 week back after Sandeep told me I'm going to make this presentation, just to double check with him. And he told me, Mr. Ganesh, we have to thank you. Had you not prepared us for tomorrow, and these are the words he used, it gave me an idea for a title for this today's topic, Tomorrow's Technology. He said, we were prepared for tomorrow. When Tesla China came to them, not Tesla US. When Tesla China came to them for supply of components, they were ready for tomorrow. So I think I can give you examples like this where so my recommendation to most of you is start getting engaged with tomorrow. Those people who got engaged with tomorrow in two steves became the greatest vacuum heat treatment people later on in life. And they bought furnaces and furnaces and furnaces and grew so big. Had they been stuck with 10x, 5x cost, what is the advantage? Where is the pollution? There is no pollution. There is no decarbonization. There is no climate change. They wouldn't have been prepared. And when that opportunity would have come, they wouldn't have been able to leverage it. I think why would a company like Mahindra would have gone in for a vacuum carburizing in 2008? Ask Sunil Kale, ask Sandeep Rege. I mean, they still run the CGCs, they still run the SQFs. When they came up with Chakan, they did not go for vacuum carburizing, they went with SQFs. But still, they went for vacuum carburizing. They wanted to be prepared for tomorrow. And I think they're seeing the advantages and benefits of those things. I think organizations like Delphi, they still run the CGC. They still run the SQF. They've gone for the third line of vacuum carburizing. There are components which are needed. They're getting ready for tomorrow. They are very sure electric vehicles will not be the only vehicles running in the world. But they're very confident that components will have to change and they will have to be ready for it. I'm sure the Mahindras, even Tata Motors, in their R&D facility, Yogesh had to go for a system. He decided on going for a vacuum carburizing as an experimental system. I asked him, Yogesh, what are you going to do with it? You're not even using it in the plant. It's R&D. He says, this is my toy. In fact, we call it Yogesh's toy today because he's preparing to get ready for tomorrow. That's the beauty of the organization. It's not easy. I've been in technology for 35 years. But it's something I think it's imperative. And I think today going forward, it's getting more and more imperative. I think climate change is on, decarbonized world is on, electric vehicles are on. Whether we like it or not, the future is staring at us. You can keep it for tomorrow, you can keep it for today, let it not become yesterday. So I have made this presentation. I think that's basically what I have to share with you. Of course, the details of any of these things that any of you need, I can engage with you on this show or later 1-to-1. Engage with your tomorrow. Let it be a better tomorrow. Avoid your future shocks. Respect your tomorrow and be prepared for tomorrow. If you need any help, this is my email ID, msmganesh@gmail.com. You're welcome to get back to me. And I'm ready to take any questions.
Mr. Ganesh, I have one question, if you permit. Yeah, recently there have been on the quenching part, the vacuum carburizing is okay. How do you foresee the difference between the oil quenching and oil quenching in vacuum and the high pressure gas quenching?
How do I see, in what sense are you talking, asking? May I know
I'm talking in terms of the quality difference. Yeah, in terms of the quality difference that it would yield
No,
in the
ultimately,
microstructure
I
on.
don't know your profile, but I'm assuming you're a heat treating person, so I won't get into the details. Why are we quenching? We are quenching because we want to achieve a certain level of hardness after you austenize the component, correct?
Yes.
You also want to quench so that you have the minimal distortion. Am I correct?
Yes.
So ideally, if I have to have both these objectives achieved to achieve my metallurgical objective as well as my physical distortion objectives, I would start with ticking both those boxes. So the simplest thing to do, or the easiest thing to do, or the best thing to do is to do high pressure helium quenching, which will, of course, you will recycle the helium because it's too expensive to let it go.
Yeah.
But by high pressure helium quenching, there are possibilities. See, let me back up. When you use steel in India, suppose we use a 16 MnCr5 or a 20 MnCr5 steel in India, the steel quality seems to change depending on which mill you get your steel from or your raw material from.
Yes. Yes.
Or your component supplier makes the raw material from. Now, this probably does not, or happens very little, say in Germany or in the US. It happens more in India. So it's quite possible that one batch lot might harden and give you the requisite requirement from helium gas quenching. The other one may not give you that.
Okay.
And in which case you have no other option but to go for oil quench. So it's your objective that is determining which one you will go for. So given a choice, if you can quench and achieve your hardness with gas quenching, I will any day recommend gas quenching because you're minimizing your distortions. And you don't have to clean your component after you quench.
Oh, so gas quenching is better than oil quenching?
No, when I say better, it has to achieve your objective first.
Yeah, correct.
And secondly, it will give you a clean component. You don't have to do post oil removal. And if the distortion is predictably corrected distortion at the soft machining stage, you can take it for assembly directly.
Oh, okay. But is there a larger cost implication, a difference?
No, the helium gas quenching is only an equipment that you need to attach to your furnace, which normally the equipment supplier will give, which is the helium recovery unit.
Yeah, okay.
There is a capex involved and a very marginal top up of helium. Marginal.
Okay.
But, so I wouldn't worry about the cost part. It is about your metallurgical requirement.
Yeah, correct. Yeah, thank you.
Welcome.
Mr. Ganesh, I have just one query. As you said, the gas quenching has got some limitation about the thicker section that won't get the core hardness. So, is there any new technology in this vacuum has come up to take care of these issues?
No, see, really, at the end of the day, gentlemen, we have to remove heat from the core to the surface, right?
Yes.
Now, that heat transfer, which goes from the core of the component to the surface, is heat transfer by conduction. Agree?
Yes, I agree.
So that is purely limited by the physics of conduction. The only conduction heat transfer is a factor of T1 minus T2. Okay, it's not T1 raised to 4 minus T2 raised to 4 like in radiation. It's T1 minus T2. T1 is the temperature on the core and T2 is the temperature on the surface. So this delta is what is driving the heat transfer by conduction. Now the only thing the equipment manufacturer can do for you is to remove the heat from the surface faster, which means I can reduce the T2. So by reducing the T2, I can keep the gradient of T1 minus T2 larger. And this can proportionately increase the Q by A, the heat transfer. So to the extent I can do that, it will help in increasing the transfer from the core to the surface. But that impact, especially if you're doing it with helium, see the problem is when you use helium, its atomic weight is 2. Now any helium which has an atomic weight of 2, all heat transfer capacities are limited by the mass of the gas. mCp delta T is the sink. So when the Cp of the helium is fixed, and mass of helium is so little that the extent to which it can draw the heat from the surface is limited by mCp delta T. The gas temperature difference between the surface temperature difference. So even if I reduce the surface temperature, I can only reduce it very little. And so to the extent it's going to reduce the heat transfer through the conduction, very limited. So frankly speaking, if you want to achieve core hardness also, which is part of your process requirement, I think you will have some challenge with helium or nitrogen or argon. You would be better off doing vacuum carburizing with oil fraction. But it varies from case to case, how thick your core is and so on and so forth.
Yeah, thank you, Mr. Ganesh. But I just asked because I have heard about or I have seen also the 360-degree cooling methods are there. Unilateral cooling methods are also there. Some people have started using, some companies, they started using the 25 bar pressure also. So is there anything really meaning by increasing only the pressure of cooling?
That's what I'm saying. Let me back up. The moment I increase the pressure in a closed system of a given volume V, Boyle's law applies. For a given fixed V, when I increase pressure, I am increasing mass. Agreed? For a
Yes.
given volume. If I have high pressure, I have high mass. When I have high mass, I have larger mCp delta T for a given Cp and a given delta T. That means I have more heat removable capabilities. High pressure means high heat removable capabilities. Because of mCp delta T, M goes up. But ultimately, the mass itself of the helium or the gas that is used is so limited, its atomic number is 2, that its impact is going to be limited. Now, of course, if your component is a slender tube or a slender shaft, you will get away with it. But if it's a larger gear, you're not going to get away with it. So it all depends on components to components. I don't think I have a blanket answer to these. Yes, it's possible. Answer is theoretically possible, but subject to component limitations.
But many people or many companies or even in India, wherever I have seen, they use mostly the nitrogen gas for cooling.
Yeah.
And very few have used helium.
No, as far as I know, most of these plants that are using vacuum carburizing and using say 16 MnCr5 or 20 MnCr5 kind of material, I doubt if they will get the surface hardness also with 20 bar nitrogen. I seriously doubt.
But maybe they are living with the problems, but I've seen they are using nitrogen.
No, maybe they are using some alloying elements which are slightly different and which gives them their hardness, or their specifications are like slightly different. It's possible.
Is that saying is true that if you want to go for a vacuum carburizing, you should go for
Mr.
the
Nitin, could we take these questions later on? We have other questions also pending, sir.
Okay.
There are a lot of
thank
other
you. Thank you,
questions
Sandeep.
pending. Yeah.
Thank you, Mr. Ganesh. Thank you.
Thank you.
You can continue.
Sandeep, please, could you take up the questions which are there in the chat?
Yeah. So how do we use these technologies of heat treating of large size components weighing 1000 kgs or above, or up to 2 millimeter diameter and not in high volumes? So how
What
do we
diameter,
do this
Sandeep?
in diameter? Is 2 meter, he says. And this diameter, how we do this in vacuum conversion?
I don't think I have any answer to that question. I have no experience, because I know the largest system that we did was some plant and facility ALD supplied somewhere in Croatia or Slovakia, but I don't think even that. That is a off-the-road vehicle kind of transmission, which were very large. But see, sometimes what they have done, and this is an experiment that we used to do earlier when off the road. I think Volvo, if I'm not wrong, Volvo in Sweden once had approached ALD for this technology, and I was there. And it was an off-the-road vehicle, a heavy vehicle. So what was then done was the carburizing was done in the vacuum carburizing furnace. The product was cooled and removed, then it was reheated and oil quenched. So they took the benefits of vacuum carburizing, but the quenching was subsequently done in conventional oil quench after reheating. But I don't think I know of any case, so I don't want to fool you by saying I have an answer to this. 2 meters and all that. I don't think vacuum furnaces have been built. I mean, vacuum furnaces we have built them up to 1500 diameter, but I don't think 2 meters and stuff like that I have heard of.
The other question is vacuum carburizing effective than SQF in terms of distortion control?
I think this subject is
I
again
think
what
you
we've been
answered.
talking.
Yeah.
First thing,
You
the
actually
furnace
answered
contributes
this.
very
Yeah.
little to the distortion.
Yeah.
The furnace only does the austenizing process. The distortions all come in the quenching system. So certainly, if your metallurgical qualities and characteristics can be achieved using 20 bar or lower pressure helium gas quench, then you will get distortion, as I defined earlier, but it will be minimal distortion and it can be corrected at the soft machining stage. But if your metallurgical requirement and characteristics cannot be achieved with helium, with the current quality of steel you are using, of course, by adding, for example, we used to make a system, and I was familiar with that system, where we would even carburize at 1080 degrees C using vanadium, aluminum, and nitrogen as adding elements, and those would get quenched faster because they were already carburized at high temperatures, but purely limited by the quenching system. So if your metallurgy needs to be achieved, whatever quenching is needed is needed. Now, if that involves distortion, but again, I want to repeat, when you quench in oil or helium with vacuum carburizing, there will be distortions. They are predictable distortions. They can be corrected at the soft machining stage, but it's an iterative process. So yes, there will be less distortion, but it will be there.
Yeah. So there is another question which is there any alternate to storage of liquid nitrogen like an on-site nitrogen gas generator which can produce 20 bar pressure with adequate volume consistently?
No, liquid nitrogen facilities are available. All these guys are providing. But again, the problem is when you're carburizing, the kind of steels you're carburizing typically, nitrogen quenching will not give you the, can be used for the blanket purpose and all the inert atmosphere thing, but I don't think it will work for quenching. For quenching, you would need helium, which will be part of a helium tank and a helium recovery system.
No, there is a question is whether we can do with gas rather than whether we can do away with liquid nitrogen and go to the nitrogen gas
Oh
generator.
yes, oh yes, oh yes. You don't need liquid nitrogen at all. It's just that the liquid nitrogen purity is a little better. But since you're not using it as an atmosphere, it's okay. So long as you have ILR2 or ILR3 grade nitrogen coming from cylinders, you're fine.
Question.
But then with 20 bar pressure, is it possible to get 20
No,
bar
that's what I
pressure?
said, Sandeep. We won't be using, I doubt it will be used for quenching. So 25 pressure would only come when you want to use it for quenching. I don't think raising it to 25 bar is going to give you any higher quenchability because that quenching curve flattens off after some time. I think 18 or 19 bar, it flattens off. I have no experience of using nitrogen at 25 bar quenching. But of course, if you are using it for quenching at 25 bar, you are better off with liquid nitrogen because the quality then matters. But if you're using it for blanket and other purposes, then ILR2, ILR3, fine. But I seriously doubt conventional 1620 mm CR5 can be hardened to the hardness level you want with 25 bar nitrogen. I seriously doubt.
So core hardness, how to increase the core hardness with nitrogen? Is it possible when we do it with 20
I
bar
don't
pressure?
think I know of that answer. I doubt it seriously, but I'm not an expert. Doubt it. Core hardness, nitrogen has its limitation. In fact, even in tool steel vacuum heat treatment, where we actually use 10 to 12 bar nitrogen for hardening tool steels, which are very easily hardenable. You know that. High-speed steel, D2, D3, H11, H13 can be hardened very easily. But even there, we have observed in our vacuum single chamber furnaces, when we cross 10 or 12 bar, we lose any more advantage, marginal advantage of quenching. Stop at 10, 12 at the maximum. I've never seen a case of, even with those easily hardenable steels. So if you're talking of carburizing steel, I seriously doubt. Sorry.
Yeah. How to differentiate the distortion taking place in for the 400 shaft in conventional oil quenching and vacuum gas quenching?
How do we differentiate?
Differentiate meaning, do we have anything which is better, and if it
Oh
is
yeah, I
better,
mean
then
that
how?
again repeated, irrelevant of your component, whether it's a linear shaft component, whether it's a round gear component, or any other blanks or anything. There is no question that the level of distortions are far lower in vacuum carburized, even if it is oil quench, and if it is helium quench, minimal. No question. The thing I'm trying to get to is if you can get predictable distortion, if you know your distortions are so many Armstrong or so many mm or whatever it is, and you can correct it at the soft machining stage, then the advantage becomes beneficial. So you can correct it and then make sure that you bring it back to normal and then do take it for assembly. That's where the advantages of the systems are, where you can get predictable distortion. I seriously doubt, I'm not an expert in sequence furnace or CGCs, build them. But I seriously doubt whether anybody who has used them can guarantee a predictable certain distortion which can be corrected previous to heat treatment. I doubt it, but I could be wrong.
I think two, three questions I'll take with your permission, and I will answer them. Does
Okay, please.
preheating also required in vacuum carburizing? It's better when you do vacuum carburizing if you preheat, because by preheating you will also reduce the heating time in vacuum carburizing,
Okay,
and
coming to
also the
preheating,
distortion.
unlike
Yeah.
unlike other furnaces, in vacuum carburizing furnaces, suppose you carburize at 980 degrees C and then you withdraw it for quenching the charge. The furnace is automatically brought down to about 700 degrees C before the next load comes in. So in that sense, there is a certain inbuilt preheating process that goes on in the same chamber. And then when the soaking takes place at 700 or something like that, then it is raised back to the osmizing temperature and then you maintain there before taken for quenching. So preheating is an inbuilt part of any vacuum carburizing system furnace design.
Yeah. What is the CP value to be maintained in vacuum carburizing, and how it is monitored and maintained throughout the process?
This is an interesting question. This is exactly what I mentioned. Unlike a sequence furnace or a CGC, you have an oxygen sensor, which monitor carbon potential sensor, which monitors the carbon potential. Uh, in a vacuum furnace, by design or by definition, there is no oxygen because it's a vacuum. So there is no sensor, there is no potential, and that's the beauty of it. And if I can quickly go back, so what we do, as I told you, is exactly what we do. We calculate for every geometry of the component that you have a batch. You calculate the surface area, you know the case depth, you calculate the carbon volume, look at the density, get the carbon mass, know its acetylene. So we find out the mass flow of the acetylene. Now I'll come to this part which I have not shown. Yeah. So if I were to draw the pulse, now I will have acetylene flow coming like this. Then I will have a gap. Then I'll have a next acetylene flow coming like this. Then I'll have a gap. Then I have a next acetylene flow coming like this. Then I can have a gap. So you see, I can adjust the frequency of the acetylene flow. I can decide the amplitude of the acetylene flow. And also, if I take this top part of the graph, it will actually be like this. Which means I can start at a certain flow and then drop the flow for the rest of that period of, say, 20 seconds or whatever it is. So I have three parameters. I can adjust frequency, I can adjust amplitude, and I can adjust the incline or slope, as we call it. So I am first giving a fixed mass of carbon. So the question of potential doesn't arise because I have fixed my carbon mass based on the surface area and the case depth. Now, how I distribute it is a matter of the algorithm, which takes the case, the geometry and the loading. And so I can decide different levels of how much I initially start high, then I can come low. Then if I want to take it high, it depends on. So what is happening is, suppose I have a gear. I'm depositing carbon here, and there is diffusion taking place through this. So based on the understanding of this diffusion coefficient, this supply has to be fed. If I excess feed it, then there will be sooting or carbon on the surface. If I can match this with the diffusion, then there is an equilibrium going on where there is no excess carbon on the surface. This is what the software does. And the beauty of this is at the end of the process of whatever time it is, when you say at 980, suppose I have to draw the temperature curve. You are at 700 and you go to 980. And at 980, this maintenance that takes place is when all this happens. This whole process is what happens here. And then once this is over, you stabilize and then you take it for quenching. So this entire process that goes on, this part is where the carburizing takes place and this is where the diffusion takes place in conventional system. But here you can do it together because carburizing and diffusion are taking place almost in equilibrium. What is coming here and what is going here. This is all due to the software or the algorithm that I told you is done. So there is no potential, there is no monitoring of oxygen content, there is no oxygen at all to monitor. So it's not an inverse of oxygen as carbon representation, it's a fixed mass carbon fluid.
So there are many questions still unanswered. Yeah. So I'll take one or two last questions, and then I think you can. Some people who wanted to ask some more questions can email it to him on.
More than welcome.
Yeah, so that he will be able to answer it. But for all participants' benefit, I'll take two more. Yeah. So how low pressure will impact the heat treatment cycle? That's the question which Amit has given. Asked, yeah. How low pressure will impact the heat treatment cycle?
No, the low pressure that I am talking of is, for example, if I put it, let me try to draw another graph. This is 1000 millibar. The horizontal line is 1000 millibar. This is the atmosphere. Now we come to 10 minus 2 millibar, which is 0.01 millibar. So this typically represents about 2 ppm of oxygen. So what we do in the system is we first pump it down from atmosphere to some 10 minus 2 millibar. So we are somewhere in this level. Then you start backfilling with nitrogen. And you will come to somewhere and toggle here, say between 7 to 10 millibar. So though we are at 7 to 10 millibar, remember we are still in vacuum. This whole thing is vacuum, this whole thing is atmosphere. So by definition of physics, we are in vacuum. This whole thing is vacuum. We are between 7 to 10 because we are toggled in nitrogen. Now, why is it we do this? Is because we want to convect the flow of acetylene in the furnace. Because by convecting it, we ensure that the acetylene flows all around the component, depending on how you stack your component. So that is the only reason why we flow partial pressure. Otherwise, we would have done it in nitrogen. Secondly, when you introduce a load in the furnace, the load is at ambient. The furnace is already maintained at 700, 720 degrees C. So in order for that load to fill up to 726 before you take it up to 900, it will help to have some convection, because we all know below 700 degrees, radiation is not very strong. Stephen Boltzmann equation kicks in only about 1000 Kelvin, about 720 degrees C. So in order to ensure that reheating of the load also happens better, we do partial pressure. And then when we fill in acetylene, it will toggle between vacuum and partial pressure. As the acetylene gets consumed on the surface, the diffusion takes as much as is consumed. This will be an equilibrium that is maintained. So in terms of partial pressure, it is only there till the load is preheated, till it reaches about 720, 730. When convection is no longer needed, it goes back to 980 for full austenizing temperature, and then it's taken over by diffusion and power.
Thank you, Ganesh. Now there's the last question. How safe vacuum carburizing compared to conventional gas carburizing?
Thanks for that question. I didn't cover it. If you see a SQF or a CGC today, what do you see when you enter the shop? First, you would enter a shop. Have you ever seen a SQF or a CGC in the machine shop? The machine shops are always clean and maybe even air conditioned. Heat treatment shop is somewhere in the corner, which is dirty, hot. So you see flames and smokes and exhaust. So you don't see anything like that in a vacuum carburizing shop. It's a clean shop. You can put it in between soft machining and hard machining also. So yes, there is no safety issue. The system is under vacuum, which means what? it is under an external pressure of 1 bar, right? It's not under any internal pressure except when it goes in the quench chamber and you're doing gas quenching. Quenching itself is about 30 to 40 seconds. If at all it is in a pressure mode, it is only for 30 to 40 seconds. And that too in a cold cell. The heated furnace is always under external pressure of 1 bar. And if at all anything happens, it will implode. Not that anything has ever imploded, because you never get scared of 1 bar pressure differential. Even thermos flask at home has a 1 bar pressure. So yeah, there is no safety issue here. There is no temperature issue because it's a cold wall furnace. The casing of the furnace is water cooled, like any vacuum furnace. You can actually touch the wall of the furnace when the furnace is running out of oscillation temperature. Can you tell me any other furnace, seal quench or CGC, which you can touch the wall of the furnace without scathing your hand when the furnace is operating at full temperature? So there is no heat issue. There is no pollution because you're only passing calculated quantity of acetylene. The only exhaust that is taken out of the plant is water vapor. There is no internal pressure of 10 bar, 20 bar exploding. And if that happens in the gas quench tank, it's for 40 seconds, but it's a cold furnace, a cold chamber, it's not a furnace. And the furnace is under external pressure of 1 bar. The oil tank is also under external pressure of 1 bar. So in terms of safety, there is no pressure issue, there is no flammability issue, there is no toxicity issue, there is no endogas or exogas, which is inherently high exothermic reaction oriented gas. There's hydrogen coming out, water vapor coming out, and that.
Thank you, Ganesh. I think some questions are still unanswered, but for paucity of time, I will not take these questions anymore. You can, the people who have asked some questions and they are unanswered can write down to him on his email ID, which he has already sent. Yeah, it's there. Yeah, msmganesh at gmail.com. And thank you very much, Ganesh, for.
Thank you all. Have a good night and thank you for attending.
Just 1 minute, Mr. Ganesh. I have a last question. First of all, I would like to thank you for the philosophical and technical talk that is possible from a graduate from IIT with the deadly degree from IIM Kolkata. My question is that most of the people were talking about distortions and all those things. After all these surface hardening processes, you are introducing carbon in austenite, which is above AC3 temperature. And then, you are quenching no matter whether you are using pressurized gas or whether you are using any cryogenic things to retain martensite to get martensite. And then you are tempering. So I hope that all these processes are being carried out in your vacuum furnace. And of course, as you mentioned, there are many advantages, so I will not go into that. But can we not use this carbon or nitrogen, not in austenite, but ferrite, as it is done in case of iron or plasma case? And there, there will be no question of any distortion because we are not going above, say, 600 or 700 degrees centigrade. So how does this process compare to this iron or plasma carburizing, nitriding, or even synergistic effect of carbon nitriding?
I couldn't hear you clearly, but if you're talking of plasma nitriding,
plasma nitriding, for example, I remember some of the Bharat Force people, they had got their crankshafts, which I remember it was made of AISI 4330. And that was an MTech project that they did at IIT. I was their guide. And we introduced this nitrogen plasma by plasma process. And we were able to increase the fatigue strength from about 840 MPa to about 945 MPa, depending on the time of this time of nitriding.
Yeah.
So it gave me
nitriding inherently is a low temperature process. So I don't think there is a major comparability to carburizing first. And it's a much longer process than say carburizing on both accounts. So I think the temperature and the time both can play a different role. And generally, I don't know, but I don't think you quench after nut riding.
No, it is not required. It is not required. But can we not introduce carbon in ferrite?
At low temperature?
Yes.
No, I don't know of that.
Okay, thank you very much.
No, sorry. Thank you.
Thank you, Ganesh. It was coming from all within, you know. Your presentation was all within. You are the major advocate of this heat treatment, vacuum heat
No,
treatment.
Sandeep, correct you. I'm not an advocate. I've lived that life. 35 years. I wish I had done things a lot differently. Today I realize, how wrongly I did it because the house of today were bothering me compared to the wives of tomorrow. I wish you people don't make that mistake. You are, of course, almost over, but the younger people don't make those mistakes. It's easy to be tempted into those mistakes.
Yeah. Yeah, but with this, onset of electric vehicle here in India, with Tata Motor coming up very strongly, with the Hyundai not far behind, even these Mahindras are not far behind. I think that is where really things will move in a different.
Even if the vehicles don't come to India, Sandeep, there will be enough component suppliers who will be supplying to the EV guys abroad.
Right.
That's also a very important factor.
Yeah, yeah. Like Tesla coming in.
Yeah, Tesla in China is sourcing from
Yeah,
India.
yeah.
Absolutely. And China is becoming not the flavor of the year for future. So India has a better potential. And I'm seeing that and sitting here in North America, how China is falling off the cliff. And India should move in, provided we are ready for tomorrow.
Yeah,
Can
of course.
we
We
use
should
solar
be ready.
energy for this vacuum furnaces?
Sorry, sir?
Can we use solar energy for this vacuum?
I have never seen that. It's an interesting thought, keeping climate change in mind, but I don't know of any companies working on that. I know we do a lot of work on solar cells, but not for solar as furnace source. Maybe control may be an issue. I don't know.
Okay, you can do this with solar energy, and that energy can be given to the grid, and grid can
Yeah.
supply
I
you
think
that
it's
energy.
for the future. Why
That's
not?
what. Yeah,
Let's
that's what.
exactly
That's
exactly the wise of if not tomorrow, day after tomorrow. Sure,
yeah. Say
certainly.
that's what Mahindra does for even wind this thing energy. We are taking it and giving it to grid, and then they are giving us some concessions.
I'm sure it's possible. Theoretically, yeah.
Yeah, it's possible. It's possible.
Correct.
Going to grid, and grid is supplying this
It's a
energy.
right way to think. Absolutely right.
Yeah, yeah. Thank you, Ganesh.
Thank you all.
Any
Have a good night.
yeah.
Let me enjoy
Any
my
last
boss.
word from our chairman?
Okay.
It was indeed a very good webinar by Mr. Ganesh, and we'll be looking forward to his presence in our MET STS next year, probably somewhere in October. So he should look into that also. We can get him as a speaker there and have a lot of contribution from him for our MET STS.
Yeah, of course.
One point to you. You told me I am not a member of ASM India. I have been a member of ASM India for almost 30 years because Prem will never let me go. So only after I retired I am around.
Yeah, he was very good friend of Prem. Yeah, and I think the new news is I think ALD ALD India, they have taken our membership.
Yes. The
Yeah,
membership has been renewed, and
yeah,
Mr.
by
Mohinder is
Mohinder
representing the company.
ALD. Yeah.
For them.
By the way, what Shashi does these days, Ganesh?
She is playing bridge with me.
Okay.
Sandeep, we have gone back to our IIT Bombay days, playing bridge, fighting with each other. Yeah. No, I mean,
he's in US?
No, he is in India. He's very much in Bombay, Amchi, Mumbai.
Okay.
Okay,
So
take care.
see
Thank you.
soon.
Good night to all of you.
Yeah, thank you. Good night. See you soon here in India.
Yeah, I'll be back. Yeah, thanks.
Bye.
Bye. Closing the
Take
app.
care.
Thank you.
Thank you.